today for our sickies. All right. So we are, as you know from the prep last night, we are talking about phase changes and the forces that hold together solids and liquids and the fact that they have to be broken in order for a phase change to occur. So just a quick reminder about properties of individual states. So a solid, very ordered, let's do water actually, very ordered and structured, stays in a particular shape. The molecules are still moving around, like vibrating, but not in a way that separates the molecule from its neighbors, okay? Once we start to warm it up, so this was at, let's see, 146 Kelvin, so plus 273. So we're talking about, like more than 100, negative 100 Celsius, okay? So liquid, now we're just above the melting point of water. So we've melted the water and it's kind of spread out on the bottom of the container. And so those forces that were holding it in a particular shape must have been weakened or completely broken in some way that allowed them to spread out over the container, okay? So not all of those molecules are being held together now. When we switch into a gas phase, so now we're above 100 C, well above 100 C in this instance, the molecules are now completely broken apart from each other. They're free to move around the container. They actually fill the entire container. Because they're not attached to each other, gravity doesn't have nearly as much of an impact. You do see some of them are congregating more lower, but they're able to move further up into the container, okay? And then also a good reminder is as we heat them up, they start moving faster and faster, okay? So remember that kinetic energy is directly proportional to its temperature. So if you heat something up, what you're saying is that you're moving those molecules around faster, okay? All right, so as we start to talk about phase changes, I basically just talked through those questions, but if you want to refer back to them, and then there's the link as well. So as we talk about phase changes, there's kind of two main things that we need to think about. We need to think about how do we increase the temperature in a particular state. So like, let's say we have liquid, and in fact, let's look back at liquid and relatively cold, and then we start to heat it up, okay? So the molecules are still in the liquid phase, but they're moving faster, okay? So we can talk about temperature changes within a particular phase. Yeah?
Does that mean the liquid is more or less viscous depending on its temperature?
Yes. Yeah. Which you guys can see that observationally, right? Like honey, right? I'm trying to think of something else. Anyway, we'll talk about viscosity in the next section too.
I observed something really interesting one time on the water, where it kind of like piled up on itself.
Yeah.
Like it was a level thing. There was a current, and so it just kind of like piled up and formed like a line where it piled up on itself.
Wait, a current? Like on a beach?
So like we were on a river. So
Okay.
On a river, so the tide was going out, and the river was going, from right to left across my dock. Right?
Okay.
My dock, the rowing team's dock.
Yeah.
And there's a section where it walks down to the water, and it's kind of like sitting on the water. And it, debris and stuff piles up there, but for the most part it was clear. And it was a really cold day, and the water kind of piled up on itself and formed a line.
Okay. And still connected to the other water, but it was like, yeah. So that's adhesive forces. This is the same reason why if you put water on a surface, it stays in little droplets and it doesn't completely separate. So it also has to do with intermolecular forces. You're leading us well into the next couple sections. But the stronger the forces are that hold particles together, the more likely they are to do that. So water has relatively high forces that hold it together. And so if you have some liquid, so the example I always use, we've got a lot of girls in here. So not that I'm being sexist, but usually girls know more about nail polish remover. So if you take water and nail polish remover and pour them out on the table, the nail polish remover is going to be very spread out, whereas the water will start to form little droplets. And that's because the water has forces holding it together. And so it's called adhesive forces. And so I can imagine if it's a really cold day, you're getting closer and closer to a solid form. Those forces that are holding the liquid together are stronger. And so it's almost becoming closer to a solid in that sense. So those adhesive forces are going to be even stronger. Same thing if you had the table, let's think of it as like a heat mat or something, and you poured the liquid on it and then you turned on the heat, those little droplets are going to start to thin out more and more. That's cool. Thank you. Okay, so I said this already, but we're talking about the forces holding molecules together. So the formal term is intermolecular forces. Inter meaning between. Think of like interstate highway or freeway. So it goes between states. The other term, like for a covalent bond, would be intramolecular. We don't ever really use that term, but we also differentiate them by calling it a bond versus a force. And then 5 seconds from now, I'm going to tell you about one of the forces' names, and we call it a bond. So it's super annoying and confusing. But recognize that we're not talking about covalent bonds that are within a particular molecule, okay? Those bonds are very, very strong. When you heat up water, or any substance for that matter, let's turn it into a gas, it's still water, right? It still has the bonds holding the oxygen and hydrogen together. It's just that the individual molecules are not held together. You are not breaking covalent bonds when you have a phase change occurring. Okay, so we're talking about the pink highlighted ones, the interactions, the forces between the molecules. And we kind of already said this, but just to reiterate it, those forces are what have to be broken for a phase change to occur. Now, when you go from a solid to a liquid, there's a lot less of them that are broken. You break, it's not as clear cut of a line. You break some of them. Usually it's the ones that are, like on the exterior, and that's why it ends up spilling down to the bottom of the container. So it doesn't allow them to keep a particular shape, but they're still held together in some form. When you talk about a liquid to a gas, there is a clear-cut line of like you are breaking all of those forces between the molecules so that the individual particles can be totally free and separate. Okay, so you're breaking intermolecular forces as we go through those phase changes. The stronger those intermolecular forces are, I kind of missed a point here. The stronger the intermolecular force is, the more energy is going to be required in order to break it. And the way that we see this, like in an observation, we can also look at things like viscosity and adhesive forces and stuff. But the main way that we observe this is by looking at melting and boiling points. So the higher a melting and boiling point is, the stronger that force is. So like without even looking at the molecule, we can just observe, okay, this one has a higher melting point or a higher boiling point. It must have stronger forces. Yeah, Lily?
So in meteorology, we were discussing the latent heat of vaporization or latent energy of vaporization.
Yeah.
Is that also related
Yeah,
to
totally.
nuclear forces?
Yeah, so the term latent heat, I'm not sure if I know exactly, but vaporization, tell me if I'm wrong. Vaporization is basically just the liquid to gas phase transition that happens when something is open. Well, it happens when it's closed, but like if you had a closed water bottle, okay, there is a certain amount of the molecules at the surface that have enough energy to break those intermolecular forces and turn into the gas phase. Not all of them have adequate energy. That doesn't happen until the boiling point, but there's always a small amount of them that are able to go into the gas phase. And the higher the temperature, the more of those go into the gas phase. So when you're talking about a climate that has water, and even in like a desert situation, but primarily when you're talking about somewhere where there's water that could evaporate, anytime you increase the temperature, more of that water, even if you're not at the boiling point, more of that water goes into the vapor phase, which is why you get humidity levels that are higher in the summer than you do in the winter. So, I was just thinking about like, what are our humidity levels like here? When we were in Houston, it's like unreal humidity there. So it's also interesting, that's a totally side subject, but when you have a lot of water in the air, it also holds a lot of heat. So you can't, this is heat capacity. When we talk about heat capacity, and water has a high heat capacity, meaning it can hold a lot of heat in it. So as you warm up an environment that's already really humid, that energy goes into warming up the water instead of just the air temperature. So like 108 degrees in Arizona might have the same amount of heat in it, the same amount of energy as 99 degrees or 98 degrees in Houston, because that water is what's holding on to the heat, just not the air temperature. Okay, good question. All right, so in fact, let's actually, I kind of think it would be useful since we just talked about that. No, I'm not ready. Okay, just keep in mind that the stronger the intermolecular force, the more energy is going to be required to break those forces apart. What we mean by that is a phase change occurring, and the way we see that is by looking at melting and boiling points. Because if it takes more energy, it's going to have to be at a higher temperature before it melts or boils. Okay, we're going to come back to that soon. All right, so that would be like observational ways to look at the strength of these forces. We're going to focus for the next little bit on looking at the molecule and its structure to predict what the forces will look like. Okay, and then we're going to bring that together and compare observational data to structure and prediction and make sure they match up. Okay, so there's three categories that we give for these intermolecular forces. Weakest up at the top, strongest down at the bottom. And within a given group, there's also a way to differentiate those. We'll leave that until Friday, because my last class we didn't get to that, so just to keep on schedule. So within a particular group, like if we have things that all fall into group 1, and how do we compare those? We will talk about that. We'll just leave it till Friday, okay? So today we're going to focus on putting a given molecule into one of these three groups. So names first. The weakest ones are called dispersion forces, and they have like 4 other names for them. So don't ask me, I don't know where the London came from. Maybe it was done in London. I don't know. London or London dispersion forces. Van der Waals. Very Dutch, Netherlands. Must have been the guy that did the work on this, or some of it at least. And then the one I like best is called induced dipole. Okay, and then the other ones, dipole-dipole forces is kind of our middle strength. And then this is why I said it's annoying. We call it a bond, even though it's technically a force. Hydrogen bonding. Okay, important to know, the weakest ones, they actually happen in all molecules. So every single molecule has these forces. It's just that some molecules, these are the only forces it has. Those some molecules are nonpolar molecules. So if the molecule is nonpolar, they only have these dispersion forces. polar molecules would have dispersion forces as well as dipole-dipole forces. Don't worry, we're going to get into what each one of these are and why they're stronger than the other. And then finally, these are also polar molecules, but they are like a special class of polar molecules where we have fluorine, oxygen, or nitrogen bonded to hydrogen. So this cannot mean that they're just in the same molecule. They have to be actually bonded to each other. So this is CO and H2. So you've got oxygen and hydrogen in the same molecule. That's not enough. They have to actually be bonded to each other. So water is like our prime example of this. The oxygen is bonded to the hydrogen. So this is going to require that if you're predicting a particular structure, you're going to have to draw the Lewis structure in order to identify are they bonded to each other or not, or at least think through it in your head. The other thing to keep in mind is you're going to have to determine polarity. So we're going to have to we'll do a very brief review of that from chapter 11. If you're rusty on it, go back and review it. But you're going to need to draw a Lewis structure and determine if the molecule is polar or not to be able to know which group to classify this in. So kind of what is that? What is that when you have like ask a question and then yes or no?
Like a flow chart?
Yes, like a flow chart, yeah. Okay, so the first question of your flow chart is it polar or not? Okay, if it's polar, then you need to look for, do we have those special bonds? And then if it's not, then you know that it's just those dispersion forces. So polar or not, if it's not, it's just dispersion forces. If it is polar, you need to ask yourself if it has those special bonds. If it doesn't, it's dipole-dipole. So these are polar molecules without those little special ones. If it does have those, then it's hydrogen bonding. Now, keep in mind, things that have dipole-dipole also have dispersion forces. It's just that they're not the strongest one, so we don't usually talk about them a whole lot. So, like, if a question says, list all of the intermolecular forces, you better include dispersion. If it says list the strongest intermolecular force that this molecule has, then just list the strongest. Yeah.
So dispersion is also found in hydrogen bonding?
Yep. So hydrogen bonding would have dipole-dipole and dispersion as well. Yeah. It's funny because hydrogen bonding is just like a special case of dipole-dipole, really. But when we talk about listing them out, we would list all three. Because something that has hydrogen bonding, by definition, would also have to be polar. And then also, is a molecule.
So why does the hydrogen make it so much more strong?
Yep, we're getting there. Okay, so we've categorized them. We've said which is stronger than the other. We've kind of talked a little bit about how to predict them. So let's talk about why is dispersion weaker and why is hydrogen so much stronger. Okay, so zooming in on our picture a little bit here. So dispersion forces, like we said, they occur in all molecules, but in non-polar molecules, they're the only force that occurs. So examples of this would be like oxygen gas or CO2, right? So here's your reminder about polarity. This bond is non-polar, so the molecule is non-polar. This bond is polar, but they're in opposite directions so that they cancel each other out, so the molecule is nonpolar. Okay, so you have this molecule floating around. It has electrons that are negatively charged. They are bonded to the nuclei, but they're moving around constantly, and they're also in the environment, right? Like they're not by themselves. So when we have oxygen and CO2 floating around in the air, maybe I like rub my foot on the carpet and have a little bit of static electricity, which is just basically electrons, right? That is now charging my foot. I don't know. Okay. So that happens. Then there's a neighboring CO2 molecule there, and it comes near those electrons. And so these electrons that are part of the CO2, they get pushed away because this is negatively charged. This is my static electricity. And these are electrons, and negative repel. So it pushes those electrons away. Okay? Well, if I've got a bunch of other CO2 molecules nearby, what's going to happen to the electrons that are next to it? Those are also going to get pushed away. Okay? All of that negative charge is going to kind of propagate, that pushing of the negative charge is going to propagate through all of those neighboring molecules. Now, this probably would make a little bit more sense if we were talking about a solid. So let's think of a chunk of CO2, dry ice, and you bring something negatively charged close to it. Okay? So those electrons are pushed to one side of the molecule, which pushes neighboring electrons to the opposite side, and it goes throughout all of the rest of the molecules. That is a dispersion force. The reason I like the term induced dipole, induced means like forced, right? It's a slight dipole. When I say dipole, think partial positive, partial negative. That's all I mean. There's a slight difference in charge. It could be a little dipole, which would be like maybe 0.2 negative and 0.2 positive, or it could be a big dipole, maybe 0.5 positive and 0.5 negative. But I just mean a separation in charge, like sides of the molecule that are positive or negative sides. Okay, so induced, it's forced on the molecule. It wasn't there, it's not permanent, it didn't exist all the time. It just, something happened to cause a slight temporary dipole. These are really small because they aren't inherent in the molecule. We're going to talk about dipole-dipole next, which is polar molecules. There is inherent polarity or an inherent charge separation that exists simply because of the structure of the molecule there. It's permanent, it's always there. Because of that, it's larger. These ones are really small, and they can be changed at any time because all it takes is just shifting the electrons around a little bit. Think of like a magnet. Like if you have a piece of metal, it just sits there, right? But if you bring a magnet just a little bit close, it's going to change the behavior of that piece of metal. It's the same thing here. It's like when it's by itself, there's no difference in charge. When you bring some other thing next to it, it starts to have an effect on it. Okay, so these are relatively weak because these are relatively small partial charges. I wanted to draw a covalent bond real quick. I'm going to put it just down here and then we'll erase it.
You don't mean like physically the molecules are smaller, you just mean that like
The charge. Yes. So think of a carbon-oxygen bond. You've got multiple electrons from the oxygen that are being attracted to 6 protons in the carbon nucleus. Then you also have the 3 electrons from carbon being attracted to 8 protons in oxygen. That is a ton of positive and negative interaction. Big positive and big negative charges. Multiple whole number charges. when we're talking about the partial charge in an induced dipole, we're talking about like 0.2 positive and 0.2 negative. Very small charges. And the bigger those charges are, the tighter, the stronger they're held together. So this is why when we heat something up, the CO bond doesn't break apart. It's very, very strong compared to slight little charges that exist between the molecule. So positive and negative attraction is what we're talking about. It's just how big are those positives and negatives. Yeah.
So I know a lot of metals have like a really high melting temperature.
Mm-hmm. Well, they're actually kind of moderately high.
Yeah.
Like this kind of stuff, molecules, covalently bound molecules, are have a really wide range, but they are probably on the lower end. So like water is a liquid at room temperature. That's a good indicator that it doesn't have a particularly high boiling point. Metals are almost all solids at room temperature. So those are kind of moderate. And then you get up to things like ionic bonds or network solids, which are covalent bonds. So diamond is a really like obvious example of this. It's covalent bonds throughout the whole solid. So when you break something, there aren't any of these intermolecular forces because there's no molecule itself. There's just covalent bonds throughout the whole thing. So you have to break a covalent bond.
Carbon covalent bonds.
Yes.
The
Yeah.
whole thing.
The whole thing. So when you want to break apart diamond, you have to find a line where there's no, this is a facet in a diamond, there's no carbon atoms through this line, and you physically are breaking covalent bonds with like force. Yeah. Same thing with ionic bonds. They have melting points that are like in the hundreds. Now, metals, their melting points are a bigger range. Those are a very different type of bond that we haven't talked about, metallic bonding. And it is strong compared to these types, but weak compared to intermolecular and covalent bonds.
Okay.
And so they're like mid-range, you know, in the anywhere from 100, 200, 300 C.
So like metal alloys, like steel or something that have melting ranges up to like 3,000 degrees.
It's because you mixed carbon in there.
Oh.
So steel has carbon mixed in. So now you're starting to get some of the properties of covalent bonding and network solids.
That makes sense. Okay.
Yeah. I'm not sure I ever thought about it in the sense of a mixture of kind of the two types, which is interesting. But yeah, that's exactly why.
That makes sense. Okay. Additionally, where would we see these things in the wild? Like, where would it like come to play in our daily lives? Like, I just out of curiosity, how would I think about this in like a word problem?
Oh, in a word problem or in your daily life?
Yes.
She's like, yes, please, both. Okay, let me give you an example. I think, no. Let's do the acetone one, right? I brought up nail polish remover. Okay, so nail polish remover looks like this. The reason I like this one is because anyone who's used nail polish remover knows that like if you get it on your hands, you don't have to go dry your hands, right? It evaporates like super quick. Water, you need to go dry your hands. The reason why is because the intermolecular forces in acetone, like just look at the structure for a second compared to water. This will lead in well to polar and hydrogen bonding. Okay, neither one of them are nonpolar, right? So they all have dispersion forces, but they must have something else too. So let's look at our categorization. So dispersion forces, no permanent dipole, just an induced dipole. Both of these, though, nonpolar bond, pretty much nonpolar bond. Polar bond here, it's trigonal planar though, and these are not equivalent to this. And so that polar bond cannot cancel out. So you've got a medium size partial negative and partial positive. Let me draw that in a different color. So I say medium size because it's bigger than the partials that were created in CO2, a nonpolar chemical, nonpolar molecule. But getting to why is hydrogen bonding so different, we definitely have partial charges in water simply by the fact, I think I looked it up in my other class. So water's boiling point is 100 C, and acetone, do I still have it open? Nope. Acetone boiling point is 56 C. Okay, so I know by observation that acetone has a lower boiling point. So question on a test, I show you the molecules. Maybe I even show you the boiling points, and I say, explain why acetone has, or select the correct answer that describes why acetone has a lower boiling point. Okay, so the basic answer is acetone only has dipole-dipole forces. Well, not only, it has dispersion and dipole-dipole. Whereas water has dispersion because it's a molecule and it has electrons that move around, so it could have those little induced dipoles. It also has dipole-dipole because it is polar. Finally, though, it has hydrogen bonding forces. And why are those so much bigger? So oxygen, nitrogen, and fluorine are the most electronegative atoms. And hydrogen is one of the least electronegative atoms that we see participating in covalent bonding. And so the difference in electronegativity is very big. Let's add that to our list down here. So big difference in electronegativity. So this is when hydrogen is bonded to fluorine, or hydrogen is bonded to oxygen, or hydrogen is bonded to nitrogen. There can be other stuff as part of this molecule. Fluorine only forms one bond, so the only time you see hydrogen bonded to fluorine is in HF. But all over biology is OH bonds with connected to some other big thing. We'll look at an example of them in a second. Same thing with the nitrogen. So big difference in electronegativity. These atoms are also really small, and that also helps to create a very polar bond. When they can get really close to each other, you can have a bigger difference in those partial charges, and I'm going to leave it at that because I don't want to talk about the other part. But that's why, like, nitrogen has a similar electronegativity to chlorine, but chlorine doesn't do this, and it's because chlorine's big. You don't have to know that, but that is why. All I want you to know from this is what types of bonds happen, and the reason why is because these partial charges that get created when those special types of bonds are there are significantly bigger. So now giving pretend numbers to these, maybe now we're talking about 0.8 positive and 0.8 negative. So big partial charges here. So back to our water example. So water has hydrogen bonding, which creates large partial charges. To even like emphasize this, let's draw them bigger. Okay, bigger than these guys. And so the boiling point's going to be higher. Other things that are come into play, this is vapor pressure, or vapor, whatever you called it, latent vapor something.
I'm going to look it up and make sure I'm saying it right.
No, that's true. I've heard the term latent heat something something. Vapor pressure is the way we talk about it. Like how much of that molecule would go into the vapor phase even before it boils. So acetone doesn't technically boil until 50 degrees C. Just to give you a reference point, room temperature is about 25. It's probably closer to like 22 or 23, but 25 is pretty warm. It's like 25 is like 78 or something. Yeah.
Pretty warm room.
Okay.
It's like 17 is a room
No, 17 is cold. Who has their room set at 65? Crazy.
You are wrong.
Crazy.
You like 70.
Yeah. Okay, so at room temperature, acetone isn't boiling, but because its forces are weaker, it's thinner, like it'll spread out more, so that's its viscosity is lower. It's what if you pour it, you can almost tell like it's a thinner liquid. It evaporates a lot quicker. You can smell it. Now, if water had a smell, then you wouldn't smell water as much. Maybe it has a smell, but we're just so familiar with it that we don't smell it. But like you can smell acetone a lot quicker than you can smell, or more readily than you can smell something. I don't know. So if you had the exact same amount, like concentration of acetone as you had like ethanol, so ethanol's boiling point is like 78 degrees C. So if you had like 50% ethanol in water and 50% acetone in water, you would smell more of the acetone than you would of the alcohol. Okay, so we need to practice categorizing. So let's not try to do all of these all at once. There's too many of them. I don't know why I did so many. So I'm going to highlight the ones I want you guys to look at. One more. Okay, so let's start with those. I want you to tell me, let's just go with what the strongest intermolecular force is, because I think you guys get it. All of these have dispersion forces. So if it's a very complicated Lewis structure, I'll give it to you. Otherwise, I'll probably make you draw it. I'm going to look up what latent heat of vaporization is.
I believe it's like how low temperature stalls on the increase until it's.
Oh, like I was talking about how if you have, no, that wouldn't be a
It's like if
vaporization.
you're boiling water, it's not going to exceed 1,000 degrees Celsius in an ideal situation.
No, yeah. Like if you measure the temperature of boiling water, it's always 100 degrees C or whatever variation based on your your atmospheric pressure. No, latent heat of vaporization is the same thing as what we're going to call heat of vaporization. Okay. It's not any different. So it is literally just the amount of energy required at 100 degrees. So liquid at 100 degrees, change that to gas at 100 degrees.
Okay.
Yeah, we'll actually do those calculations.
Fun, I've already done them.
That's great. It'll be that much easier.
I desperately need a review. It's great.
Good. Okay, so drawing Lewis structures and then following that flow chart, that apparently I couldn't remember the name of a flow chart, to determine the strongest intermolecular force. For the record, 70 degrees Fahrenheit is 21 Celsius. So I bet you, yeah, 72 is like 22. Okay, so 22 is a pretty good room temp.
If you want to like roast.
In the summer, I leave our house at like 76. I'm like, it feels cold compared to what it is outside. And besides, I'll like wear shorts or something outside, and then if it's less than 76, I'm gonna be cold inside.
Right. And then you can my mom just tells me to put on more clothes.
Yeah, I don't want to keep like changing my clothes. I'm going inside and outside.
That is, I agree. I haven't touched the thermostat back home. I'm not allowed to.
Of course not. Neither are my kids.
I have zero opinions on the indoor temperature because my roommate sets the temperature for our dorm, so
Oh, so that's why it's 70 or 65?
that's why it's 65. And then we
Okay.
get something all the time.
All right, so first question, polar or non-polar? So the only non-polar one we have is CH4. So this is the only one that has just dispersion forces or induced dipole, however you want to think of it. The other polar ones, now we need to ask ourselves, is there any, oh, I didn't give you any that are hydrogen, oh, I did on the other side. Okay, you need to ask yourself, are there any of those special HF, NH, or OH bonds? So even though there are multiple compounds that have both hydrogen and fluorine or hydrogen and water, none of them have that hydrogen or water bonded to each other. So all of the rest of these on the left-hand side are dipole-dipole. And the ones on the right-hand side, these are all biological molecules that I gave you guys so that you could kind of see how prevalent this is in biology. So there's NH bonds there. There's lots of OH bonds on ATP. Oh, I just wrote the pH ones, sorry. I meant to, they're not even like drawn out. They're just written as OH, which is really common. So an OH group is called an alcohol group. So anytime you have OH stuck on there, it's considered an alcohol. Obviously, that's not ethanol. That's just 2 carbons and OH and 5 hydrogens. Okay, so these guys over here, the strongest would be the hydrogen bonding. Okay, 2 more slides I want to look at before I let you leave. So don't forget, we want to be able to predict them from the structure. We also want to be able to make that make sense with what we see observationally. So we did that with acetone and water. So this is a similar example, but now we've got something that's nonpolar, similar in size. We'll talk about why mass matters on Friday. So this guy just has dispersion forces, whereas this one's going to have dipole-dipole. And you can see that in their melting points and boiling points. The formaldehyde has higher boiling points and melting points. And the reason why that is because of those dipole-dipole forces. And then I like this one even more. These are isomers. So an isomer is when you have same number of atoms, they're just arranged differently. So this is ethanol, we were talking about alcohols. So this is, the 2 carbons are on the end, and then on the other end is the oxygen bonded to a hydrogen. So that's why this one has hydrogen bonding. Whereas this one, the oxygen's stuck in the middle. It's bonded to the 2 carbons, but not bonded to the hydrogen. So exact same number of carbons, hydrogens, and oxygen, drastically different boiling points and melting points, though. So that is how influential that significant difference in electronegativity. Like it's a big difference in how it affects boiling points and melting points. Okay, so then on Friday we'll talk about differentiating within a group. Like what if you have two things that both have hydrogen bonding or both have dipole-dipole?
This wouldn't be the resonance structure, right? Because they're orienting themselves completely different.
Right, the bonds are actually to different atoms. So resonance structures is only when you're moving
Like the
electrons, like a bond between sets of atoms, but not moving how they're connected. Yeah. Ah, that was close.
those are so loud when they drop too. Like
I know.
One of them is a picture of you. But it's fun. I was giggling. I saw you.
I started writing a sticky note for all the questions because
Oh my gosh. I love it. I'm glad. You ask really good ones. It like, yeah. Okay. Do you
Good.
want to have the notes to reference the
I'm
questions
okay.
too?
So like crystal structures that appear in nature.
Yeah.
What kind of like reaction is forming between them? Like especially the ones that
It's
are really
just
regular.
It's just a regular or
Like-
irregular.
Regular.
Okay,
crystals.
so that is they're maximizing all of these interactions.
Okay.
So like snowflakes form because they're trying to form as many hydrogen bonds as possible. And so they end up with this, like most of them, if you look at ice and stuff, it's like a hexagon shape
Mhm.
so that you have as many of the hydrogen bonds forming as possible.
Okay. That makes sense. And then like what about I can't remember what mineral it is, but it like forms cubes. Like
Yeah, so that's probably an ionic bond.
Okay.
Yeah, and those ones are the same way. So, like, if you have sodium chloride, simplest form, so you'll have a sodium in the middle, and then you'll have chlorines surrounding it on all 6 sides.
Mhm.
And then on the other side of the chlorine, you'll have another sodium with chlorine surrounding it completely.
and it just kind of honeycombs.
Yes, exactly.
Okay, that makes sense.
Yep.
Oh, and then you mentioned smelling water. Did you know that humans are specifically adapted to be able to smell rain?